then welcome everybody. My name is Gábor Knyihár, and in the next few minutes I will talk about my research field, which is the prediction of dissolution of tablets. In this paper I published for this conference, I have investigated linear regression models, and the presentation title is, and also the article's title is, Predicting the Dissolution of Tablets based on the Raman maps using linear regression model. My co-authors was Kristóf, Csorba, and Hassan, Charaf. Please, sorry for me because I cannot switch on camera for this session, but maybe later I can. Okay, so let's get to it. First of all, before I get into the details, I would like to speak about the background of the research. In the pharmaceutical industry, one of the most research areas is the development of sustained release tablets. These tablets has a controlled dissolution process, which means that the distribution of the active ingredient is continuous. Namely, the tablet dissolved slowly and evenly to distribute this ingredient, for example, the medicine, which contains a tablet, to the body. So, for example, if you have a headache or something, this ingredient is coming in small proportions, so it is you left this problem fastly. To validate this distribution in the development of the tablets is by measuring the dissolution process, which is only possible today with a destructive measurement. And therefore, the most general quality control in this sense is sampling and investigating the pills deeply. This testing method is often ineffective because the whole set of medicines can be discarded in case of any failure or any bad results, which is significantly increase the cost of the manufacturing. So the main aim in the industry is to decrease the cost, but maintain a very strict quality requirements. So far, my main goal is to find methods to predict the dissolution process of the tablets without using any destructive measurements. There's a lot of other works related to these fields. A lot of other authors trying to predict this kind of methodology by using different inputs like crushing strength, compression force, Raman, and near infrared spectra. And they also use different methods like complex analytical modeling, neural networks, and also simulations to find the dissolution process. In this article, I'm trying to introduce another and as well very simpler linear regression model, because these methods are very complex. I mean the analytical neural networks and simulations, and need deep knowledge and many work to find the solution. But my aim is to analyze whether simpler linear regression models is also capable to predict the dissolution. So if the results are not worst relatively, then then maybe the simpler methods also can use for this. Okay, before I continue, I would like to introduce myself briefly. As I said, my name is Gábor Knyihár, and I'm a PhD student of informatics in the University of Technology and Economics in Budapest, Hungary. My main research field is medical and construction industry image processing and data analysis. This contains spectral images, computer tomography images, and many other. I wrote some article about this field. You can see some related works listing in the slide. And I also tried numerical simulation in this field, but this not achieved a good result, unfortunately. But continue to this article. To drive through this research, I'm using a reference article from Galata et al. It's titled Raman mapping based on non-textual dissolution prediction of sustained release tablets. The author of this article has made a dataset containing 28 different tablets and try to predict their dissolution process by using two different metrics. This matrix was a discretization model and with a wavelet analysis model, and the author using a neural network to predict the dissolution. I analyzed the same dataset, and this made this full article possible because I can develop my own methods and directly compare the results with the other authors' results, so I can make a conclusion what is better. So the contribution of my article is to determine a new metric for the Raman map and create a linear regression model. And as I said earlier, I can compare the results with the reference results coming from the reference article. So in the end, I can compare these results. Okay, let's jump to the technology stack and let's speak about the used materials in details. First of all, I don't know whether the audience has experience with dissolution measurement or Raman spectroscopy at all. So I would like to introduce you in this field. In the dissolution measurement, focus on sustained release tablets which are not absorbed immediately after ingestion, but evenly over 20 or 12 or 24 hours. These mechanisms can be achieved with hydrophilic matrices. One of the most widely used hydrophilic matrices is HPMC, which is the hydroxypropyl methylcellulose. These cellulose derivatives does not disintegrate in contact with water like most substances, but become in a gel-like state. This gel is slowing down the penetration of the water into the tablet, as well slow down the release of the active ingredient. These solution processes are usually characterized by a dissolution curve. You can see in the slide in the upper figure. These curves are measured by a special standardized device that dissolves the tablet in a substance similar to stomach acid. while continuously monitoring the concentration of active ingredient. This device is visible on the below figure. This measurement is usually lasts for 24 hours, and the resulting tablet, which is measured, is dissolves completely, so it is destructed. So it is not possible to make another measurement or using in other purposes. So we are using other methods like non-destructive measurement. This is Raman spectroscopy, one example for that. This is one of the most used and researched light-based non-destructive measurement. It is based on the principle of light scattering and can be used to obtain the information about the chemical structure of the surface. It's a principle that we illuminate the sample with monochromatic light, and in a very tiny amount, this light interferes with the chemical bonds within the molecules that make up the surface of the tablet, and it changes the wavelength of the reflected light. This is the so-called Raman scattering effect, and the proper detector can detect its spectrum. Typically, this is a clear fingerprint for the specific material, so we can use this technology to identify the composition of the tablets. During the evaluation of the spectroscopy, the distribution of components can be determined using different methods, like the classical least squares method, which require the reference spectrums, or with another method called multivariate curve reservation alternating least squares, MCRALS, which does not require references but not accurate as the previous one. Okay, let's speak about the composition of the tablets I used during this research. The tablets contained 4 different materials. The most important one from the aspect of the patient is the API, which is the active ingredient. This is the one that contains the medicine for such disease. The other important ingredient is the polymer matrix, the HPMC I already mentioned before. But there's 2 other components in the tablet. There is a filler, which is lactose in this case, and a lubricant material for the tablet making machine, which is magnesium stearate. The filler is the one which has the largest ratio in the tablets, and the lubricant is the less because it is needed only in a very tiny amount. In the table, you can see that I have 18 training tablets, 6 composition, and 8 tablets from each composition, and also 10 validation tablet with different compositions. The parameters from there I investigated is the ratio of the HPMC, which is the most important in this case of dissolution process. Therefore, there are samples with smaller particle size and with larger particle size HPMC. The smaller particle size is less than 45 micrometer, and the large one is greater than 125 micrometers. The dataset contains Raman maps for the tablets and also the measured dissolution curves. Every tablet has 4 maps, 1 map for each component. Here you can see the slide an example for this kind of Raman maps. In every point in the Raman maps, you can find intensity values, which is the intensity of the Raman scattering effect. But after the evaluation, it is interpreted like the intensity of one material exists in one place. The mapped area in the tablet is 1.2 times 1.2 square millimeter with 40 micrometer step size, and it contains totally 961 points. The dissolution curves, we have one dissolution curve for every tablet. The curves show the dissolved percent of API in relation with the time in 38 time points. The time points, you can interpret it the seconds, fifths, and tenths minutes before after the dissolution process beginning, and we measure this process until we reach 960 minutes. Here you can see also an example for these two to understand what is it about. Okay, let's get to the methods I used during my research. My first task was to create a metric to describe the Raman maps. To achieve this, I discretized the Raman maps and make 10 graphs of pixels. I used the formula, which you can see on the slide, to determine the groups for every pixel based on its value. It means that the pixels with a value between 0 and 1.1 belong to group 1. The pixels with value between 0.1 and 0.2 belong to the group 2, and so on. You can see two different discretized map in the slide. Clearly shows that in the case of the T30L1 sample, which contains a higher percentage of HPMC, significantly more regions can be found that belongs to the groups, denoted with larger numbers. So the more yellowish regions contains more HPMC, and the more bluish regions contains no HPMC at all. So you can see that the T10S1 samples hardly not containing HPMC, but the other is mostly yes. Second step was a custom method, which is I think the most important in this procession. It's a summary. I summarized the groups by counting the pixels in the rows and columns that belong to the same group. Here you can see a schematic example for that. So I calculated the number of pixels and summarized in a curve, and after that I am joining these values in a vector. This all process results in a matrix where every row is a material sample and every column is a parameter. But this is a very large matrix, because in this schematic I visualize only a 10 by 10 image, but in the real life this is 31 times 31. So every row contains 620 values. So after that, I'm using principal component analysis to reduce the size of the dataset to 17 principal components. So the resulting input parameter matrix I obtained is 18 times 17. After that, I obtained this input parameter matrix. I can create my linear regression model. I use the training dataset to determine the relation between the obtained parameters and the measured curves that I arrange in vectors. Using the least squares method, I achieved to find the M relation matrix in the formula with the smallest possible epsilon error. For the prediction, I use this relational matrix I obtained and find the curves for the validation dataset. Before I did this, I needed to calculate also the principal components for the validation dataset using the same transformation. And in the end, I get the predicted curves at the matrix multiplication. But these values can contain values that are out of bounds. So therefore, I maximized the values in the bounds. So I got interpretable values for every time moment. And in the end of my work, I am using such like evaluation. I evaluated the accuracy of the predicted curves, which I use F2 value published by Duan et al. In this formula, you can see on the slide RT and TT is measured on the predicted curve. So we can get F2 value, which shows how do the curves match. In case of the F2 value is 100, that this means these curves are equivalent, and this is the maximal value for this. Okay, let us speak a few words about the results. Here you can see the predicted curves of the validation dataset. The proposed methods result in an average of 47.08 F2 value, which is, I think, a relatively good result. The best case is the V30L sample, where the F2 is 73, and the worst is the V30S with 25 F2. The other curves are close to the average, as you can see in the slide. I compared my results with the result of the already mentioned Gábor et al. Article, and most of the case, the best result is coming from the reference article, which is the DI method, but there is no significant difference within the methods. The LR method is, which I proposed, is much simple and even better in some cases, like V15S or V10L samples. In general, this method is not enough accurate to use in prediction alone, but maybe if we can combine this with the other proposed methods, we can obtain better results in general. To conclude, I analyze different tablets dissolution process. I use a reference article dataset, but create a new metric based on the Raman maps and predict the dissolution curves using a linear regression model. I compare the results with reference values using an F2 metric. The results show that the linear regression cannot achieve better results than the more complex methods, but the accuracy is not much lower significantly. but the method is simpler. It's more simple. This result indicates a strong correlation between the metrics determined based on the Raman maps and the dissolution. There are still many opportunities for further development to achieve better results in dissolution prediction by examining different models. Maybe the solution is to combine the existing methods to obtain optimal results or better results. And that's all in this paper. Thank you for your kind attention. And if you have any question about this topic or for my presentation, please feel free to ask.